Welcome to this lesson on volumes with Mr. Eicher. Now you've seen volumes before in geometry. So we're just going to do some review of some of the main ideas about volumes, some of the formulas. We won't get as complicated as you may have seen in geometry. And you'll notice that we have two sections that we're dealing with, 15-4 and 15-5. It will be helpful for you if you can remember these volume formulas and know how to use them. So the first question we have is find the volume of each rectangular prism. All of the faces of the prism are rectangles, and we'd like to find the volume. The volume in this context, the volume is how many 1 by 1 by 1 cubes would fit into the shape, would fill up the shape. So you notice we have this little cube here. If I can trace that little cube. How many of those cubes would fill up this shape? Now you could count how many cubes you'd need. 1, 2, 3, 4, 5. This is 5. We have another 5 on the top, and you could keep counting how many cubes. And once you find the total number of cubes that would be the volume. Blank cubes, cubic units. If one of these little 1 by 1 by 1 cubelets is a unit, it would be cube units. Rather than counting, though, as you might remember, we could multiply. The dimension here is 5. Maybe the depth we'll call that. The dimension here is 2. There's 2 cubelets. So that means there are 10. 5 times 2. There are 10 little cubes on the top of the shape. And then how many stacks of those 10 by 10 cubes do we have? Well, it looks like this dimension is 1, 2, 3, 4, 5. 5 again. So to find the volume, we can just do the length times the width times the height. It doesn't really matter in this case which one you're identifying as the length and the width and the height. Since you're multiplying them, you're going to get the same answer regardless of what order. If you do the height, then the length and the width. So we had a 5 by 2, 5 times 2 for the top, and then we had the height, which was 5. There are 5 stacks of those 5 by 2 regions. So that would be 10 times 5 is 50. So we have 50 cubic units. Units, UN for units, units cubed, cubic units. And that would be the volume. How many cubic units can we fit in this shape? It would be 50 of them. We could do the same idea on the next question. We want to find the volume. So we have length times width times height. We have this dimension here is 3. This dimension here is 5. And then this dimension is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A very nice 10. So we would have 5 by 10. That's kind of the top of the shape. 5 by 10. And then the height is we have 3 stacks of those 5 by 10s. So that's 50 times 3. We have 150 of those little cubelets, cubic units. So that's our volume. Pretty basic. Now we'll look at 5 volume formulas, and again you've seen all of these in geometry. So let's look at these volume formulas to review. There we go. So the model is, let's see if I could change the window again. Uh-oh. There we go. The model is a little sketch, so you can get your sketch on. Prisms come in various shapes and sizes. So you could have a square prism, draw a little square, draw another little square above that, kind of above to the right of that, connect the corresponding vertices. There you go, that's pretty good. You can erase to make it look nicer. But that's the basic idea. That's a square prism. You could have a triangular. Do a little triangle. Do a little triangle. Connect the corresponding vertices. There you go. That's a triangular prism. Prisms have rectangular faces that kind of wrap around the shape, and then there are also the bases. The bases are parallel and congruent polygons. Now last year in geometry we had like hexagonal prisms. Do a little hexagon, 6 sides. Do another hexagon. Connect all those. We're not going to be looking at hexagonal prisms, but the volume formula is the same. The volume formula is the area of the base, capital B. Really important you realize capital B, not lowercase, capital B, is the area of the base, and then times the height. So for instance, in a square pyramid, the base is the square part. So you'd find the area of the square times the height, which is how many of those squares you need to stack to get to the other square base. In this triangular one, the base is the triangle, so you'd find the area of a triangle, and then you'd multiply by the height. And the height is the length that connects the two bases, the two triangles. And then the hexagon here would be the base. That would be the base. So the area, or the volume formula for a prism is the area of the base times height. A cylinder, you've seen cylinders before, a little circle, connect those. That would be your model of a cylinder. Its volume formula is conveniently the same, the area of the base times height. Now, for all cylinders, the base is a circle, so we can actually be a little more specific here. The area of a circle is ... This is when I would ask you if you could actually answer, and this wasn't a video. Pi r squared is the area of a circle, and then times the height of the cylinder. For a pyramid, you can have different shape of pyramids. We'll try to do a square pyramid, kind of do a little parallelogram looking square that's slanted, put a little dot up there, draw your pyramid. On your pyramid, the volume is 1/3 the volume of the corresponding prism with the same dimensions, the same height, and the same base. So it's not just area of the base times height, it's 1/3 the area of the base times height. Notice the similarity in these formulas. They all need the height, they all need the area of the base, but a pyramid with the same dimensions as a prism is 1/3 the volume. Now maybe if I was in class, I could show you by pouring water from a pyramid into a prism with the same area of the base and height, and I could fit 3 of those pyramid volumes into the prism. A cone, we just have a circular base, and a cone is basically like a pyramid. There you go, there's a cone, if you can see that. That's a cone, and its volume, very conveniently, is 1/3 the volume of a cylinder with the same dimensions, 1/3 the area of the base times height. And then lastly, a sphere. Draw a big circle here, draw kind of the circle like that, do a couple dashed lines, maybe put the center of the sphere. The volume of a sphere. Do you remember that one? It's one of my favorite ones. Volume equals 4/3 pi r cubed. Now this, if you remember from geometry, is based on a sum of a bunch of little pyramids. And I have this amazing three-dimensional shape that my grandmother gave me. I would illustrate. It's called the ball of wax. I don't know if you remember that from geometry. But really, this formula is based on a series. In this chapter, we're talking about series. The sum of an infinite number of pyramids, infinitely small pyramids. But rather than showing you that again, I would love to. I should probably save time on this video and move on. So these volume formulas, most of them, at least the first four, are really similar to each other. The volume of a sphere is different, but it is based on this formula here for the volume of a pyramid. And the surface area of a sphere you'd also need to derive that formula. Okay, let's look at some practice problems. Hopefully they'll be pretty straightforward for you. Let us move down here. All right. So we have a volume, find the volume of the solid. We have a cylinder here. We need the area of the base times the height. Area of the base times the height. The area of the base is a circle. The base is a circle, so we have pi r squared, the radius is 8 squared, times the height is 12. And with my calculator handy, I have 8 squared times 12. That would be 768 pi. And the units are inches, so how many cubic inches could fit in this shape? 768 pi. You can leave your answer in terms of pi. If you'd like to multiply it out, you should get approximately this many, 0.743. That many cubic inches. But again, I'm okay if the answer is left like that. With units, please. The next one, we have a cone. So the volume of the cone is 1/3 the volume formula we just used. 1/3 the area of the base, capital B, times the height. The area of base, again, is a circle. So we just have 1/3. The area of the base is pi r squared. That would be pi 6 squared. And then, how complicated. We don't have the height given to us directly. This is the height that we want, but we're given 10 here. 10 is called the slant height. So we would need to use what we know about trigonometry. This is a right triangle in here. The hypotenuse is 10. So we would have 6 squared plus the height squared equals 10 squared. This is actually a really common Pythagorean triple. It's a 3, 4, 5. 3, 4, 5 Pythagorean triple. 3 corresponds to 6. Double 3 is 6. Double 5 is 10. So double 4 is the answer that we're looking for. Double 4 is 8. So this measurement is 8. The height is 8. So times, oops, I'll do it in red, times 8. So we have 36, 6 squared is 36, a third of that is 12, And 12 times 8, I believe, is 96 pi. And I will double check just in case. Times 8, 96. 96 times pi. So you would get an answer if you want to multiply it out. 301.593. We'll round to 3 decimal places in honor of Mr. Shields, who likes that. Cubic centimeters would be our units. But again, you can leave it like that. And we have 96 pi cubic centimeters. I'd like you to pause the video and answer question number 2. So go ahead and pause. Once you have those answers, please check your work with those around you. Make sure you and they are getting the right answer. You can move on, but pause the video and I'll be back soon. Welcome back. Here's my work for number 2. Be careful, you're given a diameter, so you should use 3 as the radius. If you got something like 360 pi, you mistakenly use the diameter as the radius. And then letter B, the volume of a cone is 1/3 the volume of a corresponding cylinder with the same dimensions. So that should go pretty fast. Well, 1/3 of 90 pi is 30 pi. Now, let us move on to the next page. For number 3, we have a prism. Looks like a triangular prism. And then the other one is a pyramid. So let's look at these. Recall how to work with these. So with a triangular, this is triangle here, triangular prism, the volume formula is the area of the base, which is the triangle, times the height. Now this height that I just mentioned, that height is the height of the prism. That's the length that connects the two triangular faces. And that length is 4. So we know this height is this 4 right here. We just need the area of the base. The area of the base is the area of this triangle. So the base is the area of the triangle. Area of triangle. The area formula for a triangle. The area formula for a triangle is the base of the triangle times the height of the triangle over 2. It's based on a parallelogram, half of the area of a parallelogram. Base times height over 2, also known as 1/2 base times height. That's how I learned it back in my day. So here we have the base of the triangle is 3. 3. The height of the triangle is 1.5. Not 4, that's the height of the prism. This is the height of the triangle, which is 1.5. And then over 2. So we'd have 1.5 times 1.5. I'm going to guess that's 2.25, but just to make sure. Oh, good. 2.25 is the area of the triangle, the area of the base. So we have that area, 2.25. We come back up to here. So the volume would equal 2.25 is the area of the base times the height of the prism. The height is 4. Ooh, mental math, that's 9, I believe. 4/4 is 1. 2 times 4 is 8. 8 plus 1 is 9. Volume is 9 cubic centimeters. And that's the volume of the prism. Let's consider now the volume, stray mark. Let's consider now the volume of the pyramid. Volume of the pyramid. So a pyramid, we have the volume is 1/3 That 1/3 is probably the most common part that would be forgotten. 1/3 the area of the base times the height of the pyramid. The height of the pyramid is given. The height of the pyramid is 10. Now we just need the area of the base. The base is this, which, because of perspective, looks like a parallelogram. It's really a rectangular base. That's 12 by 8. So the volume actually is pretty fast. Everything's given to us, so we just multiply the dimensions. 1/3 the area of the base, 12 by 8, times 10. Not sure why I'm writing off the screen when I have so much white space over here, but these things happen. So the volume equals, let's see, 1/3 of 12, I could do that, 4 times 8 times 10. 32 times 10, 320 cubic feet. Thus is our answer highlighted. So, here we are coming to a close. I would like you to try on your own, or with your neighbor, 4, 5, and 6. You'll notice 6 is talking about a sphere. You do have the volume formula on the front page, so plug those values in and get those answered for 4, 5, 6. Once you've finished 4, 5, and 6, please compare your answers with your neighbor, and I will come back soon and show you all of the answers. So please pause this video until everyone's ready to check out the answers. Thank you. Here we are. Number 4, I got 60 cubic feet. Number 5, I got 48 cubic centimeters. And number 6, I got 36 pi cubic feet, also known as 113.097. Hopefully those were pretty straightforward for you. The last topic we'll look at is what's known as Cavalieri's principle, which deals with volumes. I'd like you to chat with your neighbor to see if you could figure out, based on these pictures that I've given you, what is Cavalieri's principle telling us? What is the principle? How is it dealing with volumes? What do we mean? What do you think Cavalieri discovered about volumes when the shapes appear, such as these? So pause this video, take a couple minutes to chat with your neighbor to see if you could figure out what this principle might be illustrating. Looking at the stack of quarters on the left, the volume of the first stack of quarters, the volume of the first stack, is the same as the volume of the second stack. Even though this one is kind of like a nice orderly pattern here for the volume, as long as there's the same number of quarters, same height of quarters, and each quarter has the same volume, as long as those are true, then this volume has or is the same as this volume. So this volume would equal this volume, as long as they're the same height of quarters and each quarter has the same individual volume. That also applies over here. This stack of what are called CDs, this stack of CD cases at least, this stack has a certain volume. This stack has the exact same volume, volume 1, volume 2. These volumes are the same as long as you have the same number of CD cases, the same height of CD cases, and each individual case has the same volume. So this principle is very helpful because if I told you you have a cylinder and the height of the cylinder is 10 and the radius of the cylinder is 2. It doesn't matter if the cylinder is a right cylinder kind of meaning standing up straight like this first stack of quarters. It doesn't matter if it's standing up straight or if it's an oblique cylinder, like this, as long as this height is the same, 10, and this radius is the same, 2. As long as that's the case, Cavalieri's principle tells us that this volume, number 1, is going to be the same as this volume, number 2. So it doesn't matter if it's a right cylinder or if it's what's called an oblique. You might have heard those in terms of muscles, your obliques, or an oblique cylinder. So in the lines here, we have if two solids, let me get rid of all this writing here. If two solids have the same height and the same cross section is what we call that. The cross section is like each individual quarter or each individual CD case. If two solids have the same height and the same cross section at every level, then they have the same volume. And that is Cavalieri's principle. Thank you for watching this video about volumes. I look forward to seeing you soon, and good luck on your homework.